So let's do a quick review of what we covered in that notebook. You could say that the quasi-random search methods have sort of the best of both worlds of grid and random search. We've got grid and random on the two left columns, and then we have the quasi-random methods on the right columns. And with grid search, we get systematic gaps in our search space. With random search, we get large occasional gaps in the search space. And when we move to the quasi-random methods, we tend to get smaller pockets. And so less of, and that aren't systematic. So we also talked about discrepancy, how that is a measure of uniformity to assess how well a number of samples have done space filling or uniform space filling, where higher discrepancy values are less uniform and lower discrepancy values are better and more uniform. And we also talked a little bit about how the size of the pockets or some of this discrepancy metric increases with the number of dimensions. We talked about how for a square, the diagonal along the square is larger than the side length of the square, and then the so essentially that's the max spacing that we have, or helps kind of to quantify our gap in a grid search. And as we move to higher dimensions with 3 parameters and 4 and n dimensions, or sorry, d dimensions here, that kind of maximum distance or that gap in the middle gets larger in the higher dimensions. And then real world materials optimization problems tend to have very limited budgets and many dimensions. Think about the periodic table, for example. There's 118 elements to choose from. And then think about you as a scientist being in the lab running an experiment, something that might take you a few hours or maybe a week or 2 weeks or even a month or so, just for a single iteration of this experiment that you're trying. And so here we're looking at a fairly data limited case with 10 experiments and then 100 experiments and then 1,000 experiments for increasing numbers of dimensions, where you'll notice in the middle here that the quasi-random methods, and this is the case for essentially across everything, the quasi-random methods have lower discrepancies, or in other words, are more uniform than the grid and random search. And you also get these cases where usually the Latin hypercube with the optimization that I mentioned in the notebook is typically doing better than Sobel. And that random usually has a lower discrepancy than grid search. So one of the things that might be surprising is that typically random search is actually a better way to go than grid search when you're looking at trying combinations of, instead of doing a full factorial design where you divide everything into a grid, if you were just search across your parameters randomly, then often you can optimize your objective property, your property of interest more efficiently. So next, I'm going to be talking about adaptive experimentation and specifically Bayesian optimization. So what adaptive experimentation means is that you're using prior information to inform future decisions. Some other synonyms for this are active learning, sequential learning, adaptive design, and informed search. And they all basically follow the same analogy where you initialize your campaign, your search campaign, based on what objectives you want to optimize, what parameters you want to tune, and any constraints on that space. Then you have your planning phase, your experimenting phase, your analysis phase. You continue that loop until you reach some criteria, your objective has been met, or you've ran out of resources, and that concludes your optimization. And here's a quote from Citrine Informatics. Not all experiments are equally useful. Some experiments provide more information than others. With adaptive experimentation, each new experiment is chosen in order to maximize the amount of useful information. Whereas with those other methods, uh, you're not uh, really quantifying that difference in usefulness, except that you want to try out points that are kind of different from each other. And some terminology before we dig into some of the details here. Acquisition functions. These are mathematical techniques that guide how the parameter space should be explored during optimization. Exploitation focuses on results in the vicinity of the current best results by penalizing for higher variance values. You want to exploit the best performing things that are there, as opposed to exploration, where it pushes the search towards unexplored regions. So you have oftentimes acquisition functions will leverage this trade off between exploitation, what you think is really good with a high certainty, and exploration, the things that you don't really know about and so might be worth testing out. Bayesian optimization is a particularly effective way to trade off between exploitation and exploration, where one of the common acquisition functions used is called expected improvement, that rewards evaluation of the objective based on the expected improvement relative to the current best observed objective. And here you can see in this Gaussian process model, which is usually what's used under the hood for Bayesian optimization, is that you get these mean estimates of the model. This is some parameter of interest plotted along a 1D parameter space. So sorry, a performance metric versus the design parameter. You have the data, in this case, 5 data points. You have your means and your uncertainties there. And this is the formula for expected improvement. Essentially, what was listed there, the expectation value of the max between some point that you want to look at minus the best you've observed so far, and you just make sure it's above 0. If you get something that's less than 0, then you just throw it out. And what Bayesian optimization does is it chooses the point with the maximum acquisition function value. So it looks, there's many ways to do this, but you look through all sorts of values for x, and you try to find the x that maximizes your EI of x. So on the bottom here, we now have expected improvement plotted as a function of that 1D parameter space. So we've looked at many different values for our parameter, and we look to find where the maximum expected improvement is, and that's the red dashed line shown there. And then we do this iteratively, where as you add new data, you look for the new maximum expected improvement based on the refitted model, and your uncertainties are decreasing and your model predictions are getting more accurate as you continue these iterations. So next, we'll look at doing some optimization benchmarking between the traditional methods that I mentioned, the grid and random search and the quasi-random search, and comparing that to some Bayesian optimization, and to see which one is more efficient. So for this next notebook, we'll be looking at informed sampling via Bayesian optimization, where informed means, like I talked about earlier, that it uses information about the objective function to be optimized. Now let's talk a little bit about objective functions. To make this a little bit more concrete, an objective function might be the efficiency of a solar cell, where you want to maximize the objective function, or in other words, maximize the efficiency of the solar cell. You could also have, along with that same solar cell, another objective, being the cost, where you want to minimize the cost. And when we start talking about objective functions, then discrepancy is no longer a satisfactory measure of performance, because we have new information that we can use. So for this one, we're going to use an analytical function, basically a mathematical formula called the Branin function, along with a limited evaluation budget. And we'll use that Branin function as our objective function here. And we can evaluate this 2D Branin function by just passing in 2 parameters here, 2.0, 3.0, and out returns the function value. Then we can also define the total number of trials, in this case 20, and also take a look at this function. We can visualize it because it's in 2 dimensions, so that makes it fairly easy. We'll go ahead and do that here. So you can see that it has a wide range from around 0 to up to 300. It has this large peak off to the side here, another peak here. But we're actually interested in minimizing this function. So let's take a look at this in a log scale to get a little bit better idea of where those global minima are. And so we can see one kind of up here at the top, one here in the middle, the bottom, and one in the lower right-hand corner. So this is where we start using Meta's adaptive experimentation platform, and there are many other very good platforms for doing Bayesian optimization. This is my personal favorite. It's one that allows a lot of flexibility in terms of the building blocks it gives. It's open source, and there's a large amount of support, developer support, if you run into issues by people working at Meta. So the simplest API is the loop API, and you can use this via the optimize function. We'll define our objective name as the Branin metric. We'll define an evaluation function, which takes in a dictionary of parameters and returns a new dictionary with our objective name corresponding to the actual function value evaluated each of those parameters. From here, we'll define our search space using the parameters keyword argument. So we've got the name, the type of the parameter, and then the bounds on it. For x1 and x2, we'll use the evaluate function that we defined up here, pass our objective name, tell it to minimize it, give it a search budget, and set a random seed so that we can run these results reproducibly. And we can see that the optimization is progressing, and it will stop at 20 trials. As the optimization progresses, as we get more trials, more information, it becomes progressively more difficult to fit the model with data. Bayesian optimization is usually not a very scalable approach, and so if you start dealing with thousands upon thousands of data points, or tens of thousands of data points, then it's usually better to look at a model like genetic algorithms, and you're also typically looking at a lower cost per evaluation if you're able to run tens of thousands of experiments. But Bayesian optimization does very well in the limit of low data. So we can take a look at the best parameters that we got during the optimization, as well as plot that up against our our solution space here. And we'll notice that what the algorithm determined to be the best parameter is very close to one of those global minima. We can also take a look at the model itself, looking at the mean predictions and the standard deviations associated with those. So what you see in gray are the in-sample points, or in other words, the points that the model actually sampled during the 20 iterations. And you can see that the Gaussian process model is using those points to inform its predictions here. And then you can also see like I mentioned, the standard errors there. In this next segment, we'll take a look at comparing the efficiency of searching based on the different sampling methods that we use. And since the Bayesian optimization API is different from the functions that were defined previously, here we'll create a function for extracting the parameters and their objective values. And so you can see that we get this pandas data frame with our x1 and x2 parameters, and then the Branin function value or objective, in our case, associated with each of those. And we can also take a look at visualizing the best objective so far as a function of the iteration number. In other words, we'll look at a line of the running minimum the iterations progress. And you can see that we start out with something kind of high, and as the optimization progresses, we are able to successfully minimize the objective function to a low value. And when we're comparing to methods that do systematic sampling, in particular grid search, in order to make sure that we're making a fair comparison, when I run these repeat campaigns, I'm going to add some jitter or a shift in the x and y of the bounds of the objective function to uh, with grid spacing being at fixed locations to kind of help get some randomness associated with the objective function, since the randomness isn't there in the grid search. And so you can see where normally it was -5 to 10 and 0 to 10, it's added some jitter to the bounds there. This next part will take some time, so we'll skip ahead. But the idea being that we'll run 50 repeat campaigns. We'll define a different seed, random number generator seed, for each of those campaigns. We'll get a new set of noisy bounds. We'll optimize our parameters, and we'll store the results in this list here. And here we can take a look at the results of the Bayesian optimization experiments run over 50 repeats, where we have the best parameters, the values, meaning the mean and the standard deviations associated with the best parameters, an experiment object that contains our data and a lot of other information related to the optimization, as well as the model that was used for it. So we've got all 50 of those rows quantified, and we can use a couple helper functions that we've defined to calculate the running best objective, as well as kind of store some of the useful data that we need here. And now that we performed the 50 repeat campaigns for Bayesian optimization, we can take a look at the average behavior across the campaigns. Now, this was the main reason for doing the repeats, was to look at the average behavior and then sort of the variation across multiple campaigns. And so that's what we're seeing here, where you have the, let's see, we're taking a look at the objective function as a function of the iteration number. And early on, you've got very large variances, and as the optimization progresses, typically the algorithms are matching each other. Sorry, the different search campaigns are matching each other in terms of performance a little bit more. So with the Bayesian optimization results computed now, we can also compare with the other search types. And this will go through and essentially grab 20 trials or samples using each of the 4 sampling functions: grid search, random search, Latin hypercube with the optimization, and Sobel sampling, and do that for 50 repeats, similar to the Bayesian optimization. And after we compile the results, the traditional design of experiments and the Bayesian optimization, we can do some data wrangling with the data frames in order to split those into individual data frames associated with each of the each of the seeds, and compute the average, compute the standard deviation. And once all those results are combined, we can plot them all together here. And that's what you're seeing here, is this comparison between the 5 different search methods that we've talked about so far. And as we hover over this, we can see that, for example, on the 12th iteration, that grid search was the least efficient. By that point, random search was the next best, followed by Sobel, followed by Latin hypercube, and finally with Bayesian optimization being the most efficient here. Now, there's a lot of information here, so we can remove some of this and gradually add it back in. So if we take a look at just, for example, Bayesian versus grid search, you can see that it's maxing out at the 16 functions because of that discrete sampling involved with grid searches, the constraints there. But that the Bayesian optimization is doing much better than that. And we can also take a look at some of these quasi-random methods and see that early on, it's kind of within the first few iterations, there's a pretty small difference between the different search algorithms. But starting around, excuse me, the sixth iteration is when Bayesian optimization starts to really improve the optimization efficiency past that of the other methods as well. So we can also go to higher dimensions, and so there's an analytical function defined in 6 dimensions called the Hartman-6 function. This has 6 local minima in contrast to the Branin function, which was 2-dimensional and it had 3 global minima. Since we can't really visualize this, I'll just show some of the math involved for that function and comment on a few other characteristics here. So with in particular the global minimum being given by this value negative 3.32 about at this particular set of points for x, and the bounds are 0 to 1 for this function. So similarly, we can define a new evaluate function, set a new objective name as Hartman-6 or whatever we want to call it, and return a dictionary mapping from the objective name to our scalar value for our Hartman-6 function. We need a new search space here that includes all 6 of our parameters. It's sort of a verbose way of doing it, but it could be kind of condensed with list comprehension. And then same as before, we have our evaluation function, our objective name. We want to minimize, and we set the total number of trials. In this case, we'll use a slightly higher total number of trials, 50 instead of 20, and take a look at the results there as well. And as before, each optimization will give it a different random seed to ensure both reproducibility, but also make sure that each optimization is doing something different, kind of a different starting point. We'll follow kind of the same trend as before, where we're looking at the other sampling functions, compiling all the data together, and take a look at the final performance here. So with this early on, each of the methods are really performing about on par with each other up until around 10 or 11 iterations here, 12 iterations. And at that point is when you really start to see the Bayesian optimization performing well, where essentially the Bayesian optimization is figuring out what the solution space looks like based on the limited number of trials, and then efficiently locking into the minima there. So to summarize some of our optimization results, we looked at 2 analytical functions, 2 mathematical formulas, essentially. One called the Branin function, pictured here. You can see the linear scaled values in the 2-dimensional search space, and then log scaled values to give you an idea of the 3 global minima that are here. We ran this for 50 repeat campaigns, and for each campaign, we added some noise to the bounds to help with making a fair comparison between the different algorithms. And what we saw is that in general, grid was performing the least efficiently, this was followed by random search being more efficient, and then Sobel, Latin hypercube, and finally the Bayesian optimization being the most efficient of the chosen methods. And we've also looked at the Hartman-6 function, a 6-dimensional analytic function that has 6 local minima. And towards the beginning, each of the algorithms are pretty much on par with each other. But around iteration 12, we start to see that sharp decrease in the objective function, or in other words, better values of the minimized objective function for Bayesian optimization.